Hello, my dear students, and welcome back to the second or maybe the third part of this chapter and the second part with the oscilloscope. In the previous part, we were more oriented toward the understanding the general block diagram of an cathode ray oscilloscope, and we focus on the triggering, how we synchronize the trigger, the input impedance, the probe effect, the AC and DC coupling modes, and so on. Herein, in this last part with our chapter, we are mainly to study two important modes related to the oscilloscope. The first is the external trigger. Maybe in the previous part, we already illustrated the importance of the trigger as it is responsible of tracing the signal from the extreme left point to the extreme right point. And we also study the importance of having a synchronized trigger where this synchronization is established from the input signal so that we can generate a pulse synchronized with the input itself so that we ensure that our trigger sawtooth signal is synchronized with the same point of intersection with the signal, and this ensure continuity vision for our observers. However, if you recognize this graph, my dear students, you will find something very tricky, that although by ensuring that our triggering signal is synchronized with the input signal, we are misleading our observer in terms of phase. Why? If you observe this signal, you will find that the signal starts from this point every time. This is from the observer point of view. So if you are in an exam and I told you, please determine the phase of this sinusoidal signal, simply you told me, okay, this signal starts from this angle, which is something between 0 and 90, because this is a 0 and this is a 90. So let's say this is a phase of 60, for example. But realistically, this signal is a 90-degree phase signal. This is the real start of the signal. However, the internal triggering mode is not capable to determine the real starting point of the signal, because simply it is related to the point at which the threshold voltage, this one in red, hit or intersect your sinusoidal signal, which is obviously not the real start point of the signal. That makes us reach a conclusion that in an oscilloscope, we are not capable to determine the real phase of a signal as far as we are using the internal triggering. What if we would like to measure the exact phase of a signal? Here, we should start our sawtooth signal here, in this point. So instead of starting the sawtooth here, you should start it here, so that it captures the real starting of the signal, which is the real phase, which is -90, for example, in this case. So you will not be able to adjust the internal trigger because simply this is a built-in feature in your oscilloscope. However, you have the capability to insert your external trigger where, in this case, you as a user who is responsible to guarantee or ensure the synchronization in terms of frequency, of course, as well as in terms of phase. So you are going to start the sawtooth exactly in the same time as the input. And that's why if the sawtooth starts here and the input starts here, then you capture the real phase of the signal. That's why in our oscilloscopes, we have this feature where I'm just giving you the choice. Either to use my built-in triggering, which is here, or use your external trigger, and in this case, you are the one who is responsible to ensure the synchronization in terms of frequency and phase. So this is the first point to mention. The second point to mention in this third part of the lecture is what we call the XY mode. In the previous part of our chapter, we were only concerned about what we can call a time-dependent representation. So usually we insert a triggering signal in the X variation, or what we call the horizontal variation, in order to ensure a scanning of the point from the extreme left, from the extreme left to the extreme right. And our input signal to be sketched, to be represented on the oscilloscope, is inserted on the vertical variation, for example, this sinusoidal signal. What if I would like to insert two signals so that I am representing a difference between two signals, not a time-dependent representation? This is what we call an XY mode. So in the XY mode, we have an input signal, a time-dependent input signal in the vertical axis, as usual. And in the horizontal axis, where we used to have a trigger, we will not insert a trigger. We are going to insert an X of t, or a signal function of time. Let's see what will happen. So let me go here. So this is the oscilloscope screen. Here is the vertical variation, and here is the horizontal variation. So in the vertical variation, I'm going to insert, for example, 5 sine omega t. And in the vertical variation, again, if you remember in the previous part, we already do the same, but we insert here trigger. Now I am not going to insert a trigger. I will insert also 5 sine omega t. And again, this is 90 shifted representation. So I will start from this point. This is the starting point. T equals 0 here and t equals 0 here. Now, going slightly to point number 1, for example, here 1. So what happened in 1? This indicates that I'm moving toward right, and this indicates that I'm moving up. And because both signals are typically the same, so I will move up and right with the same value. So this angle is typically 45, because delta y and delta x are the same. And I will continue to reach this point. And then I will return back to the same path. And then I will go on down to reach this point. So what I'm going to represent here is simply a straight line with an angle 45. So once you have a straight line with an angle 45, this is an indication for what? This is an indication that your x value and your y value are typically the same. This maybe comes to the question why we are using XY mode. So you can now answer the question. We are using XY mode for this example, in order to examine the phase shift between X and Y. So if you insert a signal in X and then a signal in Y, and the output on the XY mode is typically a straight line with a 45-degree inclination angle, that means that both signals are of the same amplitude, same frequency, and the same phase. So here we are examining 3: phase, amplitude, and frequency. So phase, amplitude, and frequency, yes. So now we can synchronize this. Let's see what happens if we change the phase between X and Y, we change the amplitude between X and Y, we change the frequency between X and Y. Let's see. So herein I will use this nice virtual tool. As you can see, we have 2 inputs. This is the input on the X, represented by A capital sign A small t plus phi. And this is in the Y, representing B capital sign BT. So A and B representing the amplitudes of A and B. A small and B small are with a frequency embedded because A is 2 by F and B is 2 by F. And phi simply is the phase between A and B because B with 0 phase. So In the first example, I'm going to make everything equal. So I will start with both have the same frequency and both have of the same amplitude. And start with angle equals 0, phase equals 0. Again, please just take care that here everything is radian, so that's why it's a bit confusing, but let's make it a number. So, okay. So as you can see here, this is typically what we already got that this is simply a straight line with a 45 degrees to the right, indicating a typical input x and y. So typically x is equal y. What happens if we change the phase? So we will start first to change the phase. So this is what will happen. So it's now an ellipse. It's now ellipse still. Yes, let's stop here. Here, this is an equivalent to pi over 2 or 90 degree 90 degree phase. So whenever it's pi over 2, we have a circle. So this is a circle. It represents what? Represents a 90 degree phase shift between A and B. Let's continue. Again, it will turn to an ellipse. And now let's see this point. So now this point is negative pi shift. So the shift between A and B in terms of phase is 180. So it gets a straight line again, but with negative 45 degree. Now, so again, we have a circle. This circle represents a shift of 270 degree, which is simply negative 90. And now, again an ellipse. So this is returned back to our 2 pi, which is 0. You know, 2 pi shift is typically the 0 shift, which is again a straight line. So if we go to our slides here, this is 0, this is 180, and this is 90 or 270, as we already demonstrated. And here you can see a generic clock representation starting from 0, 45, 90, and so on, till we reach 0 again. So you can understand that if you already know that your input signals, X and Y, are of the same amplitude, the same frequency, but you need to represent only a variation in phase, you can use this XY mode in order to determine typically the phase shift between X and Y. Although using the normal default trigger, you will not be able to determine, as we already studied, the exact phase of X and the exact phase of Y. But using this XY mode, you can determine the phase shift between X and Y. Maybe you can ask me, okay, but if we have an angle, not 45, not 135, any random angle between 0 and 360, is it possible to determine the phase? Yes, you can go to this equation. This is generally for any elliptical Lagrange figure. We call this Lagrange figure. So for any elliptical Lagrange figure, you can determine the A and B ratio, with B is the intersection point with the y-axis, as you can see, this blue line, and A is the greatest diameter of the ellipse, the extreme diameter here. So by dividing B over A, you can determine the phase angle between the X signal and the Y signal. So generally, for any signal or for any value, you can determine the X and Y or the phase shift between the X signal and Y signal using this Lagrange figure. Okay, what if now we consider, if you remember, we mentioned that we are using XY mode to distinguish the X and Y in terms of 3 parameters: the phase, the frequency, and the amplitude. We already examined together the variation in phase. So now for this case, A and B have identically the same amplitude, identically the same frequency, but we just change the phase from 0 to 360. Now, what if A and B have the same frequency, the same amplitude? So amplitude, I will, sorry, the same frequency, the same phase. So I will keep here the phase as 0, and they have different amplitude. So I will change this, for example, to 120, and I will change this, for example, to 50. Let's see what will happen. So a straight line again. And now, when we reach that 90 phase, this is the 90 phase, instead of having a circle, it turns to be an ellipse, which is logic. Because simply when A is equal to B, the X component is equal to Y component, then we have a circle. But now, as you can see, A is much greater than B. So it's no longer circle, it's an ellipse. So if you have an ellipse like that, then you can say, okay, it's a 90-degree shift, but it's simply a 90-degree shift of two different amplitudes, because simply we have A, and we have the vertical alignment is not as equal as the horizontal alignment. That's why our amplitudes are not the same. So here you can distinguish between different in amplitude and different in phase as well. So let's see the third case, which is maybe the most interesting case. So I will return back to 100 and 100, and I will maintain the phase, not automatic. So I will make the phase 0. So now both are with the same amplitude, but I'm going to make, for example, B signal with double the frequency of A. Oh, this is what happened. If you recognize it well, it's very logic. Why it's very logic? Because in the time where the horizontal signal makes one cycle, the vertical signal makes two cycles. That's why we have two loops, or this figure of 8, Les Ajouts figure. So how we can determine this? Let's go to the presentation here. So it's very simple. When you just see more than one loop, so in this previous example, it's always one loop, either a straight line or a circle or whatever it is. Once you see more than one loop in your Les Ajouts figures, simply start to plot vertical line and horizontal line and determine the number of tangent points. You know, tangent, which is the intersection point between the line and the edges of these loops. So as you can see here, we have two horizontal intersections. So two horizontal intersection, which is Fy, on one vertical intersection, which is Fx. Again, let's think about it. That means that the frequency in the Y is double. So in the time where Fx make one loop, Fy makes two loops, because simply it's double frequency. So simply the ratio of frequency between Fy and Fx is 2/1, which is 2. So here you can again not only determine the phase shift, but also you can determine the variation in the frequency. So for example, this is 6 examples here. If you make a line here and like here, so this is 2 intersection with respect to 1 intersection. So this is 2/1. Let's make it here again. So here we have this one here, and here we have this one here. So as you can see in this example, we have 2 intersection. Use the annotate to make it a bit easier. Line. Okay, so I will draw a line here. Okay, let's not make it in red so that you can distinguish colors. So let's make it, for example, in blue. So here I will plot a line here. I will plot a line here. I will plot a line here. It's not so good. It should be tangent. So here line and the bottom line here. And let's see. Okay, so here we have one intersection here and one intersection here. So in the x direction, we have two. In the y direction, we have 1, 2, and 3. So the ratio is 3 in Fy to 2 in Fx. So the ratio is 3/2. As you can see. So Fy over Fx is 3/2. Let's do it the same here. So here one. As you can see, this is the same point. So 1 here. If we make it here. So we have 1, 2, assume it's tangent. I'm sorry that the line is a bit far from the curve. So 1, 2, 3, 4. So it's a 4 vertically over, 4 horizontally over 1 vertically. So 4/1. Let's do it here. So horizontally, 1, 2, 3, 4, 5. Vertically, 1, 2. So it's 5/2. Let's do it here. So here we have 1, 2, 3. And here we have so again 1, 2, 3, 4, 5 horizontally, and we have and we have 1, 2, 3 vertically. So it's 5/3, which is 2.5/1.5, and so on. Here, of course, you can see 1, 2, 3, 4, 5 over 1, 2, 3, 4. So it's 5/4, and so on. So you can make it in this way, where you can make it either with an x line and y line and see the intersection points to know which the ratio between fx and fy. So now you can see that using this, we can distinguish the number of the ratio between frequencies, or the ratio in between phase, but just take care of a very small important note here, that when we make a comparison in phase, we assume that the frequency is identical. When we make a comparison of frequency, we assume that the phase is identical. Of course, you can make two of them are variable, and this is, you can examine it here. For example, if here I 7 and 12, and let me now move the annotate. So let's see, as you can see here. But of course, this will make your Lissajous figures more and more complicated. So usually, when we examine this in the exams, for example, I just make it a bit easy. So just either to have a constant phase with different in frequency, or a constant frequency with a different in phase. But it's relatively challenging to make variation in both frequency and the phase simultaneously, because this will relatively makes your capability to recognize the Lissajous figure more and more difficult. That's all for this lecture. So I think now we are done with the analog measurements, including different analog measurements, starting from voltmeter, ammeter, up to oscilloscope. Now it's time to go to chapter number 3, where we are going to consider the frequency measurements and the spectrum analyzer. Thank you very much.